this is the last of the Thursday seminars, so we're glad to have Eric wrapping things up for us. And take it away, representations of motion groups.
Okay, thanks very much for attending my talk. I know you have a choice when Zooming seminars these days, so I appreciate that. So I understand I have an hour plus, maybe up to an hour and a half. So anyway, I'll try to keep it around an hour. So what I wanted to talk to you about is, well, it's a kind of special quantum symmetry that hasn't gotten very much attention recently. But we've looked at it some, and there has been some work. So I'd like to tell you about this. So I'll be reporting on some joint work with a few people. So Gustafsson, Kimball, and Zhang, there's one paper, and then with Bolivant, Kimball, and Martin, another paper, and an older paper with Kadar, Martin, and Wang, and then another paper we're working on right now, which will be coming out soon. So right, very good. So let me just dive in. So let's give a motivation. So the 2D picture we feel like we understand relatively well, and one of the key aspects of the sort of two-dimensional topological physics, etc., is Braid group representations. So in particular, in the sort of condensed matter setting, the statistics of anyons in two-dimensional topological phases form braids and hence give rise to braid group representations. And this connection is very tight and useful. For example, understanding the unitary representations of the braid group and the closures of their image is all tied up in the question of universality of the topological quantum computer. And moreover, of course, going back several decades, braid group representations are key in constructing invariants of links and of three manifolds using typically the Markov trace. And moreover, if we're thinking about the setting of 2+1 TQFTs, then the braid group corresponds exactly to the genus 0 part of this story. So passing up to 3 dimensions, considerably less is known, but I would like to argue for you that the correct thing to use in place of the braid group is something called motion groups. So I've sort of drawn these pictures over here that should illustrate kind of what I have in mind. So, right, the usual thing for in 2 dimensions is you have a surface with punctures or with marked points, and then in 3 dimensions you might have a 3 manifold with some embedded links. And exactly in the same way that we study the braid groups on surfaces, we'll try to study sort of the motions of these arcs and links inside a 3 manifold. So there's lots of questions to think about and to keep in mind as we go. So one is this useful in physics at all? And the fact is that there are some guesses that yes, there's some use, that in 3-dimensional topological phases of matter, one could have loop-like excitations, and the motions of these loops would sort of, well, potentially be useful in quantum computational models based on 3-dimensional topological phases of matter. And then, of course, one can ask the usual questions from mathematics about whether there's interesting topological invariants that we can associate. And then the other question that I think is really in the back of all of our minds is the 3+1 TQFT situation. And so anyway, we'll make some contact with what's known in that area. But in some ways, kind of thinking about, like in the 2-dimensional picture, how the braid group representations how interesting those representations are is kind of related to how interesting the 2+1 TQFT is. Well, potentially these motion group representations will have something, will give us some sort of idea about that. So I kind of think of it as a canary in the coal mine situation for 3+1 TQFTs and how interesting they may be. So here's some definitions of motion groups. So you could ignore all the text and just look at the heuristic definition on the left there. The idea is, well, we have loops or links or knots, and they can move around in some three-dimensional space. So to be exact, we go back to work of David Daum in his thesis from 1962, which was followed up in some papers by Deborah Goldsmith in 1981, 1982. And so the idea is the following. Think of a motion of some oriented compact submanifold of another oriented manifold. It's just an ambient isotopy of n in M, so that sort of the initial place is just the identity on M, and the final place, the final f sub 1 should carry n into itself as a set, and in fact as an oriented submanifold, as we'll see. Just to point out something, so it's not the case that if you restrict to n, that it's the identity on n. It just needs to carry it in sort of set-wise. So now if, so certain motions are boring. So the motion, so the ambient isotopies that leave n fixed set-wise for all t is called a stationary motion. So you can think of like the motion of like a hula hoop, just sort of turning around and around. That's a stationary motion. And so we use the stationary motions to construct an equivalence relation on motions. So we say two of these are equivalent if you take the inverse of one, compose it with the other, then that should be homotopic to a stationary motion. And so the motion group is exactly motions modulo this equivalence. So I'll give a little bit more information about this in a moment, but that's the basic setup. So some more details, some different ways of thinking about this motion group. So we start by looking at the homeomorphisms of the manifold M with some special properties. And you could think about diffeomorphisms instead, and sometimes that's the right thing to do, but we'll sort of for the moment just think about homeomorphisms. So the C here refers to compact support. The boundary of M must be fixed pointwise under these homeomorphisms. N should be fixed setwise as a set. So it can, if it has components, those components can be permuted, for example, but as a set, they should come back to where they were. And this is, so certainly the orientation on M should be preserved. And for me, I'm going to consider the case where the orientation on N is also preserved. So now you can think about motions as paths inside those compactly supported homeomorphisms on M with some additional properties. So of course, F0 is the identity, and F1 now we can think of as being a like one of these homeomorphisms that fixes in setwise. And then you can
Eric,
actually, sorry, yes.
Hi, this is Kevin Walker. Can I ask a question?
Sure.
So what's the motivation for insisting that the orientation on N be fixed? Because that's not imposed by the TQFT. If this was coming from a TQFT, that wouldn't.
Right. So this is just for simplicity.
Okay.
So yeah, so certainly one can consider the situation where like you have a circle that with an orientation and you turn it upside down. That would change the orientation. That's a perfectly good motion, but just for today, I'm going to only consider, so it's really just for simplicity. Right. So yeah, so in this case, another way of describing the motion group is you can describe it as a relative fundamental group in this way. So this is yet another construction. And then there's another one that one can think about, and that's what we call H plus of M comma N. So this is, right, just take this original sort of relative homeomorphism group and look at the sort of pi zero, so the path connected components based at the identity on M, and also the plus here corresponds to orientation preserving, which, as Kevin points out, isn't always something we necessarily need, but we'll assume it here. And so now we can use this to help us understand this motion group. So there's a map, delta, which simply takes the class of F and sends it to the class of its ending position, F1, between these spaces. And in some cases, this is actually an isomorphism. So if M is R3, for example, this is an isomorphism. It's always going to be surjective in the case of the 3 sphere. But in that case, it's not quite 1-to-1. It has a kernel, which is a Z2. So you don't lose much, but it's another way of describing it. So there are lots of ways of studying these. That's useful. There's still more, so let me make a few more remarks. So,
sorry, Eric, just real
yeah.
quick. In that last assertion at the bottom, what is N? Is N just empty?
Yeah, so N should be anything in this case, any submanifold.
Oh, wow. Okay.
Yeah, I think this is in the thesis of Goldsmith, I think. But yeah, so this is known. This is certainly in these papers. Of course, what we have in mind is to have a link inside S3.
Of course.
But
yeah.
But yeah, that seems to be quite general.
Wow. Okay. Thank you.
Somebody can correct me if I'm wrong, but I think that's what the papers say anyway. Yeah. So yeah, so some remarks and subtleties about this situation. So right, so as we saw, sometimes we can consider M to be compact, and sometimes we won't. You might consider the situation where the boundary of M is not empty. That's possible. There's a question of orientation, as has been brought up. You might ask for diffeomorphisms instead of homeomorphisms. In 3 dimensions, it mostly doesn't matter, but there are some subtleties. And of course, this is perfectly reasonable to consider in any dimension. So for this talk, I'll focus mostly on the 3-dimensional manifold case, but also the 2-dimensional manifold. But as I say, any dimension is okay. And so we'll focus on the 3 sphere, the 3 ball, and R3. So these are 3 situations, or the similar 2-dimensional situations. So one thing that one always has, which is quite useful, is you always have an action of the motion group on pi 1 of the complement of N inside M, acting as automorphisms. And it's sort of the obvious way, right? So you can just think about, in 3 dimensions, it's quite easy. You can just throw your loops around the complement, or through the complement of N in M, and then do your motion, and you can see what's happening to your generators of your fundamental group. So it's quite a useful way of understanding these, and particularly for getting presentations. So perhaps surprisingly, there aren't very many presentations of specific motion groups available in the literature. And it's really only recently that they've shown up. So maybe the first one is a disjoint union of circles. That one has been done going back some years. And rather recently, Damiani and Kabbalah considered the situation where you have a disjoint union of hop flinks, 2-component hop flinks, and possibly some circles. So they have a presentation. This picture here, which is called the necklace, where you have a bunch of circles confined to another circle. Bellingeri and Bodine considered this one. And then also torus links were considered. And that's mostly what we know. So there's plenty of work to be done, and it's quite interesting how little is known in comparison with the Braid group situation. So let me just quickly go through some examples. The details aren't too important. I should point out that the Braid group obviously fits into this situation, and in fact is quite close to what Hurwitz originally formulated as the Braid group of sort of monodromy. And so of course we have the presentation, and so this is just sort of show that the two-dimensional situation can be thought of in this context. So that's just the Braid group. One of the most interesting ones is the situation of the loop Braid group. So this is where you take, for example, the 3-ball and a bunch of disjoint circles, and you can construct this motion group called the loop Braid group. And in this case, you can see the presentation. You have two kinds of generators, one where one circle passes through another, and another where the position of two circles are interchanged. And the sigma I satisfy the Braid relations, whereas the SI satisfy the symmetric group relations. And then there are some mixed relations as well. And this last one, notice there's some asymmetry in this relation L2. You could also instead, depending on your conventions, sort of turn these around, but you can't have both simultaneously. Okay, so that's an important one. That's the loop Braid group.
So, Eric, this is Vaughan.
Yes.
Is
Yes.
that related to virtual links? But also, they also have these mixed things.
That's right. Yeah. So so there's something called the virtual Braid group, and there is a relation, and there's these forbidden moves, and in particular, I think L2 is one of the forbidden moves. So this is let's see, am I right or am I wrong? Yeah. Anyway, so certainly there's a relation, and I forget which one is bigger. I think the virtual Braid group is bigger. So this has an extra relation, I think.
So this is a homomorphic image of the virtual Braid group.
I think that's right. I'm getting confused. It might be the other way, but I think that's right. Yeah. Someone can correct me if I'm wrong, but that's, yeah. So yeah, I think we throw in some forbidden move and get this. Right. Yeah. So there's certainly, yeah, there is this relationship, and there's some papers maybe that connect them. Right. So the next one that's kind of interesting is this necklace Braid group. And so this one also sort of contains the Braid group. So it's contained in the way where if you have two of these adjacent loops and you take one and you pass it through the other one, that's a motion. And then you can also take all of the loops and shift them all by one around. And that motion is called tau. And here are the relations. So it contains something like the Braid group. Well, it contains a small Braid group, but then it's really the circle Braid group because there's this mod n thing happening. And then the shifting by tau sort of conjugates the Braid motions around. And notice that this is a 2n, not an n, and that has to do with the fact that we're sitting inside the 3 sphere. And so a full shift around is not, so shifting tau n times looks like the same thing, but in the motion group, it's a different motion. That has order 2 and is central, turns out. So that's another interesting example. Another example that has been studied recently are torus links. And I won't go into the details here too much. I think what I've drawn here would actually be TL33. And so you should glue this up with a 2π/3 twist on the ends. And so then there will be 3 components, a green, a blue, and a red. And they are unknotted, but linked, kind of like the generalization of Hopf link. And again, the Braid relations are satisfied by the interchange of 2 components. So this again contains something like the Braid group. There's another operation, which is the sort of the rotation of the ith component by 2 pi over p. In this case, I think they're all going to be trivial. You can show that they're basically stationary, but if you had more strands, then maybe they would be non-trivial. So this one was studied some by Goldsmith, and then more recently in a paper by Chu and Wang, they looked at torus links very carefully. So let me make some remarks about motion groups. So as I said, sort of what we would like is to have representations coming from 3+1 TQFTs, but that's generally not too easy to understand. However, we do see that the Braid group is quite often a subgroup of a motion group of some link. And so we can think about extending. And that's, in fact, what we'll do. A future hope would be that maybe you can get invariance of sort of knotted surfaces sitting inside R4, much in the same way that you get invariance of knots by tracing out braids in the disk. And finally, there are some physicists that are thinking about this situation. So this is just a small picture from a paper by Levin and Wang in PRL. And so they're studying the possibility of sort of these vortices in sort of topological vortices and the motions of these things. So anyway, so certainly there's some potential for physical applications. So now let me do a bunch of reviewing of representations of the Braid group, because this is a good source. Before I do that, maybe I'll pause and see if anyone has any questions. Okay, yeah, so this part of the talk, I'm going to just go over some representation of the Braid group that are known. So, of course, Rowell's representation. So he's not often pictured in talks, so I thought I'd provide a picture of Rowell. So this is a representation he sort of discovered in 1936, and it's exactly this matrix representation, where T can be thought of as a variable. And there are lots of interesting interpretations of this representation. And until the 1980s, this was essentially all we knew. And then in the 1980s, there was sort of an explosion of new representations. And I'm not going in chronological order really here, but certainly the Yang-Baxter equation provides representations of the Braid group. And I've sort of described it here. And I call these representations local because they sort of only algebraically locally exchange adjacent pairs. And in the 1980s, when von discovered his polynomial invariant, then that was using quotients, so finite dimensional quotients of the Braid group algebra. And so in particular, like the Temperley-Lieb algebra, and then a bit later, the Hecke algebra. And then not too much long after that, there were Berman and Wenzel and Murakami discovered another finite tower of finite dimensional quotients of the Braid group called BMW algebras, has 2 parameters. And so anyway, so these are some representations that we could think about trying to extend to motion groups. Let me say a few more. So, right, again, in the 1980s, Drinfeld's work on quasi-triangular, quasi-Hopf algebras provided a lot of representations sort of through Yang-Baxter equations, essentially. And then after that, it was realized that there's a categorical way of thinking about this. So if we look at braided fusion categories, you take an object X in C, then there's a algebra homomorphism from the group algebra, the Braid group, to the algebra, the centralizer algebra, or the algebra of endomorphisms of X tensor N, using the braiding. here. And then the Braid group acts on this direct sum by using composition with the endomorphism algebra. So this is a faithful representation of this algebra. And so, right, so we get an action, the Braid group using this. Another interesting representation that has become kind of popular recently in sort of in this quantum computing setting, topological quantum computation, is this metaplectic representations. And so here we're looking at an algebra that might be called the quantum torus, but the idea is it has a bunch of generators, UI, and they sort of next near neighbors sort of Q commute roughly, and otherwise commute, and then they have finite order. So this was in this paper of Jones and Goldschmidt. And from this, you can get a representation of the Braid group sitting inside this algebra by sending the generators sigma I to this thing here. And Jones called this the Gaussian representation because of this term here, I think. So this is another kind of interesting representation that we might think about trying to extend. Let me briefly mention one more setup that was kind of recent, but inspired by those results. And so the idea is the following: you fix a finite group G and a abelian, and a bihomomorphism from G cross G to Zm, and then some root of unity. And you can construct something called the iterated twisted tensor power. So an algebra that just takes the group algebra of G and twists the tensor product over this. And this is the way the twisting goes exactly, using this setup. And so it very much mimics this metaplectic representation. And in fact, that is an example. And so then you can look for Braid group representations sitting inside this iterated twisted tensor power. And you can just go ahead and try. The two that Jones already knew about, one is the metaplectic one and the other is this quaternionic one, can be constructed in this way. And anyway, it's a new idea, but it particularly lends itself to the question of trying to extend representations. So yeah, maybe I'll stop here because that's the end of what I'll talk about for Braid group representations. Maybe someone has another favorite Braid group representation that they would like to mention. I'm happy to hear. Yeah, Lawrence Kramer Bigelow. That's a good point. So it will get mentioned in a moment. I can mention that they actually do show up in a very secret way here. So the Lawrence Kramer Bigelow representations are in particular representations coming from BMW algebra. It's a particular diagram. So great, yes. Okay, so what about categorical connections? Let's see, is that where I am? Yeah, okay, so let me just step back a bit and say what we can say about sort of categories. So far, right, we're mostly just talking about Braid group representations, but what are the connections? Well, so in this paper that Reuter mentioned in his talk a couple weeks ago, pointed out that if you look at a semi-simple 3+1 TQFT and a spinless, so a four manifold that doesn't admit spin structure, then the invariant associated with a four manifold only depends on classical things like fundamental group, the Euler characteristic, signature. So that kind of gives maybe a hint that representations of motion groups coming from 3+1 TQFTs, maybe we shouldn't expect much. Maybe we don't expect just everything to, every nice representation to show up. There were some efforts in this direction. So Liang Cheng showed that you can get loop braid group representations from a pair of objects in a braided fusion category if their tensor product is a direct sum of bosons and fermions. But this one really is trying to just lift a two-dimensional story to a three-dimensional story, because you're just using the usual braiding on X tensor Y, taken multiple times. And moreover, his results essentially show that if he can get representations, then the braided fusion category is weakly integral. So conjecturally that gets finite image. So in particular, maybe not super interesting, but anyway, it's a technique that's been tried. Another categorical construction, so the one that everyone sort of can get a handle on, is this Digraph Witten theory. So there's there's such a theory in all dimensions. And so Zhenghang Wang and his student Yang Qiu provided some evidence that if you look at the representations of motion groups that you would get from 3+1 untwisted Digraph Witten based on a finite group G, then these are actually determined by those coming from the corresponding 2+1 Digraph Witten theory. Excuse me. So, right. And in particular, they studied torus links with the boundary labeled by pure fluxes. So that's a particular kind of object, I guess. And they also study mapping class groups of closed manifolds. And so it's an interesting question to see just how general is this situation. Is it true for, you know, all motion groups and all mapping class groups for Digraph Witten? And more generally, what happens for other 3+1 TQFTs? Is it still just determined by something essentially two-dimensional? Maybe something even classical. So that's an open question. Another way to think about this is, a couple of them anyway, is what about sort of loop braided fusion categories? What can you do? So a very naive guess would be, well, we just take an object but in a braided fusion category, and of course it's not interesting unless it's not symmetric. And then you have a braiding, C. And then can you also have another symmetric braiding so that they play nicely together? So that would be to try to get a representation of the loop braid group. Sort of the braiding part, or the loop sort of leapfrogging, would be corresponding to the interesting braiding, and then the symmetric braiding would take care of the other part. But it's really quite unusual in a braided fusion category to have more than one braiding on an object X. And this is made very explicit by results in a paper of Dmitry Nikšić. So in particular, if C is like modular, typically you won't have any symmetric braiding on it at all. That's kind of the general story.
Eric, can I stop you for a moment?
Yes.
This is Victor Ostrich. So one example of category where you have kind of two braidings, I know you can take representations of some group like SL2, and then it has symmetric braiding, but it also has kind of Greenfield braiding, which is kind of deformation of the symmetric braiding. So are these two braidings compatible in a way you want? Or no?
Yeah, so I think, right. So then the question is, what category are we looking at?
So
right?
categories, it's not finite. It has infinitely many simple objects, but it's semi-simple, nice categories.
Yeah. So right. So in particular, not fusion, but
It's
yeah.
not
So
fusion.
actually, that's yeah. So actually, that would be quite interesting. I think that's one direction that we should explore. I think that what I want to say is studying the things that we sort of already know very well, like braided fusion categories, maybe won't get us very far. And in fact, we need to relax some conditions. And finitely many simple objects might well be one such thing to do.
Oh, yeah, I'm willing to sacrifice this.
yeah, absolutely. Yeah, so that might well be a good direction to try. And we'll see later that non-semi-simple is also a possibility. Another direction is to think about loop braided vector spaces. So it's kind of the same story, but now we're looking at instead just a vector space. So we look for two solutions to the Yang-Baxter equation that play nicely together. And this can happen, and it happens certainly happens when your underlying braided vector space RV is of group type. In other words, you get a Drenfeld module. In that case, if you just take sort of the obvious S that just swaps things, that will work. And this really is sort of harkening back to the Digraph Witten situation. So yes, you can do this, and we have lots of examples where you can, but they all, again, seem to be coming from finite groups in some way. And from what I can tell, typically if you have a solution to the Yang-Baxter equation that is not of group type, then it probably doesn't extend in this way. So here's kind of a chart of what extensions we can manage. So on the left column is the braid group representation, and then the other two columns are the loop braid group and the necklace braid group. You can see that the necklace braid group is somewhat easier to deal with. But certainly the Rowell representation extends to both. The Lorentz-Kramer representation, you can extend it to the loop braid group, but the parameters have to be chosen very carefully in such a way that it makes it essentially trivial in many ways. On the other hand, the necklace braid group does have a nice extension of the Lorentz-Kramer representation. As I mentioned on the previous slide, local representations, so coming from the Yang-Baxter equation, it works for the loop braid group if it's of group type, but otherwise maybe not. On the other hand, the necklace braid group, you can always do it. If you take an arbitrary, completely reducible representation of the braid group, some complex representation, there are lots of counterexamples to cases where you cannot extend loop braid group to the loop braid group. You can always extend in that situation to the necklace braid group, but it's not always in a very interesting way. It's essentially a central extension. Looking at the paper of Tuba and Wenzel, where they classified braid group representations of dimension less than 5, where the braid group is on 3 strands, turns out we can prove that all of those do extend to the loop braid group and also to the necklace braid group. But interestingly, this 5 is a sharp bound. There are irreducible representations of B3 of dimension 6 that do not extend to the loop braid group. So it's interesting that that's the cutoff. These Gaussian or metaplectic and the quaternionic representations of the braid group seemingly don't extend to the loop braid group, but they do extend to the necklace braid group. And also all of those ones that I mentioned in this new paper where we construct representations coming from these iterated twisted tensor products, the story is essentially the same. I think we can always extend those to the necklace braid group, essentially because of this situation. But to the loop braid group, it seems harder. Categorical constructions that we know that are relatively easy to write down. So if X and Y are in a braided fusion category, this result of Liang-Chang here shows that rarely you can extend to the loop braid group. And for the necklace braid group, if Y happens to centralize X, or they centralize each other, then you can find a representation acting on the centralizer of this object. So this is essentially what's known.
Eric, this is Vaughan again.
Yes.
One thing that occurred to me that you haven't looked at in the braid group things are these set theoretic solutions or racks and things like that. Do you have any information on that?
Yeah, so I think that those essentially fall into this Yang-Baxter setting, right? So these can be, you can turn these into.
I suppose that's true, but they're quite special in that class.
Yeah, it's true. Yeah, so these are you thinking of the involutive ones or just the general ones?
General ones.
Yeah, right. Yeah, I think that, again, I think that those should extend to the loop braid group, because I feel like one could put those into the context of group type solutions. So I think it should be doable. I don't know if it's been studied very carefully, but I agree that could be very interesting because of the connection to invariance in particular through racks. That could be very good. So thanks for that comment. Let's see, I think there was something in the chat. Right, so the Lawrence Kramer, right, so Celeste knows about this more than I do. So it doesn't extend by taking the same matrices, but there's some other construction. So this hasn't been attempted to my knowledge, or has it? So Celeste's knowledge on this is a superset of mine. So I think that, yeah, as far as I know, I was just thinking of exactly what Bardakov had done, that there was severe restrictions on that. And essentially they don't work, which maybe is also a clue that that it won't work for the BMW algebras in general.
Yeah, I don't know if it was very clear what I wrote. What I meant is that the matrices in the representation come from homological construction. So it's not really surprising that the same matrices don't work if we just use them for the sigma generators and add permutation matrices for the row generators. What should be attempted to know if it actually extends is to do the homological construction on the loop braid group in a topological way. So no, maybe now it's clear.
I see. Yeah, that's clear. Yeah, that certainly could be interesting to try. But right, yeah, very good. Thank you. Our next project, Celeste. So right, so here I'll get to the work with Celeste Damiani and Paul Martin that we're working on now. So one thing you might try is to try to find finite dimensional quotients of the group algebra of the loop braid group. And maybe you want to try the Hecke-like thing, just take a quotient by these things. And unfortunately, that's not finite dimensional. And so that makes us sad. But there's something that you can do. And this is quite interesting. So one thing to point out is that this algebra, although it is infinite dimensional, the extended Rowell representation, so the Rowell representation extended to the loop braid group, is a representation because it has these two eigenvalues. That's really all you need. Right, and it looks exactly like this. So what do you do? Well, you send sigma I to the usual Rowell representation, and then Si, what do? You evaluate sigma I at t equals 1. So it gives you this permutation matrix, and that is the extension. But if you look at the relationships between these matrices Mi and Pi, they satisfy some extra conditions that are interesting. In particular, if you take the product of these two, and in the other order, take the product of these two things. So they have a chance at vanishing because of the eigenvalue conditions. And they do, in fact, vanish for the Rowell representation. So now what we're going to do is we're going to define the loop Hecke algebra to be the quotient of the loop braid group, not by just the Hecke relation, but by these additional quadratic relations on the generators. This turns out to be finite dimensional. So this is pretty interesting. And so, right, so this was exactly inspired by the Rowell representation. So this will also have a representation that is the Rowell representation, but of course it'll have more. So let's discuss that one a little bit. So what are some of the properties of this loop Hecke algebra? One thing to note right away is it's not semi-simple, okay? One can just compute, has a Jacobson radical. Moreover, it does admit a local representation, and it looks a little bit like the Rowell thing, but here, this is a 4x4 matrix, R is, and notice that in the lower right-hand corner, we put a minus T. Okay, so this is a solution to the Yang-Baxter equation. And again, we'll take...
Eric, there's one. I thought that was just the exterior powers of the Bureau representation.
It may well be, yeah. But this, so this actually, so the Rowell representation has, right, it just goes up in dimension by 1 each time. And so, yeah, so this one goes up by 2. And so, yeah, you're right. It's probably just this. I hadn't known that connection. But there is, of course, another, you could take, I guess, plus T here instead. But that's a very interesting connection that I hadn't known. So if we take R and evaluate it T equals 1, then that's going to be the S that we'll use. And so now you can look at the representation of the loop Braid group that you get by using this sort of local thing. And we call it the loop Rowell-Rittenberg representation. Yeah, so it turns out that this is a representation of the loop Hecke algebra. It's important to point out that this is not unitary. And as far as they know, so it's not unitary for any choice of T except for perhaps some trivial ones like plus or minus 1, maybe. Okay. So this gives a representation of the loop Hecke algebra, and so we can study it. Right, so what is its structure? So we're going to look not at the loop Hecke algebra, but we will look at the algebra that we get as an image of this representation, which we can prove is actually a faithful representation for small values of n, but we don't yet have a proof in general. But how does it look? Well, right, so the algebra looks exactly like this. It decomposes in this way. So you can think of it as some matrices. Along the diagonal are these sort of simple algebras of dimension n choose I squared. And then along the upper, the first upper diagonal, we get some additional modules or algebras, parts of the algebra of dimension, the product of these things. And that the red part is exactly the Jacobson radical. If we take this loop Rowell-Rittenberg algebra and mod out by the Jacobson radical, then we get, of course, exactly the semi-simple part that's along the diagonal. And its Bradley diagram is interesting. It's exactly Pascal's triangle. And so that's what I've written in green. And then the red parts are sort of the dimensions of these A's that show up in between. Okay. Right, so we know something about the structure of this. So what else can we do? So just as sort of points of discussion, this non-semi-simplicity seems to be a feature. So if we look at 3 plus 1 TQFTs that are semi-simple, maybe we don't expect much to come out of those. But maybe the fact that this is non-semi-simple is the reason why it's interesting. Should mention maybe a more robust categorical approach is still needed, since we don't know that much about representations coming from different categories, sort of a higher categorical approach. This is sort of the first finite dimensional quotient of motion group algebras that we can get that are sort of reasonably interesting. So that's an area that one should move towards. And one might also consider topological invariance of surfaces, so of some kind of ribbon surfaces sitting inside a 4 manifold. So those are kind of ideas that one could consider. Let me say a little bit more about this topological invariant part. So you might wonder if you can just put a Markov trace on LHN. Okay, so what does this mean? Well, we want a linear functional so that, right, all of these are satisfied. So in particular, now we have sort of 2 of these stabilization rules. So we have sigma n and Sn. And so when we add sort of one strand on, and then of course we'll adjust by the rise in order to get an invariant. And of course, then we want the trace of 1 to be 1. But if you actually look at the relations that we find on LHN, we find that there's a relationship between the trace of like a single braid and a single swap, Sn. And this is it's this relation here exactly. And either of the 2 solutions that you get lead to the trivial invariant. So it seems like Markov traces on this are sort of a dead end. On the other hand, it should be remembered that the Rowell representation, if you want to get an invariant from it, you don't take a trace, you take a determinant of something, right? That's how you get the Alexander polynomial. So at least there are lots of other things to consider. And with that, I'll thank you for your attention.
Thanks, Eric. Excellent. So are there more questions for Eric?
Can I just ask, Eric, there's one thing that wasn't quite clear. When you do those R matrix solutions, that you could also take the R matrix as sigma and then just use the permutation matrix as S. Does that work to give us a representation of your, what was it?
Of the loop braid group, yeah. So this slide here is exactly that point. So here, this right. So you can see that's exactly, so S is exactly the swap. So that works, but it only works if your R is of group type. So if you take some other solution to the Yang-Baxter equation, those mixed relations, it turns out, kill this possibility in most cases. So it's quite interesting that you can't quite do it all the time. For the necklace braid group, the thing exactly that you would expect, where you just you take sort of the full twist for tau, which is the sort of the that one actually does work. So this is how we can extend any Yang-Baxter operator to a representation of the necklace braid group. But for the loop braid group, it fails spectacularly in some cases because of these extra mixed relations.
Well, I certainly myself am feeling like I'm like trying to flip through your slides on my iPad to digest more, but perhaps anyone who wants to can join us in the tea room for more informal chat. And let's thank Eric again.